Hi everyone, welcome back. Just want to let you know, some people are asking about how to use my videos. I've just done some help on that. Also, I have hundreds, over 400 videos, and that goes right through from year 7 to 12. So all you have to do is scroll down my page and find virtually any topic you want. Someone from India asked yesterday if I could make a video on integration and area under the curve. Now, I realised that I didn't have anything on that. I've got lots of videos on how to integrate, but I don't have anything on area under the curve. Trouble is, when someone from overseas asks me for a topic, I don't know what sort of detail they need. The concept of area under the curve is massive. It goes into all sorts of things that you can do, area between two curves, just simple ones, and then you can get more and more complicated. So I'm going to have a go with it and talk about what I normally talk about when I introduce this topic and some of the things I do to try to bring it to life. Now, there is a proof for this, but I'm not going through the proof for it. If I find a good link in someone else's video, I'll add that in so you can have a look at the full proof. But I will talk about it in concept. Here's the graph of y equals x squared plus 1. And I've made it a little bit more spread out here because that's what a lot of mathematicians do. But the scales are different. The scale there is different. Each one of these is 1, whereas going across each one is a half. I've coloured in that red area. Now, traditionally, what I understand, what I believe happened, is people knew that they needed to calculate shapes where they needed that sort of area. So when they're calculating that, they could simply make up a whole lot of boxes and count the boxes, and the smaller boxes, the more accurate they could do. But what they actually did was made lots of skinny rectangles. Now, a lot of you should have already learnt that, but if you haven't, there's lots of skinny rectangles. If you made 10 skinny rectangles, you could get a fairly accurate approximation of that area. We go a step further and we put 10 that are under the graph and 10 that are over and get the average of them. We won't go there, but you can make 100 of them. And you can talk about skinnier and skinnier rectangles to calculate that area. Now, let's go here before I forget. If I put the x value of 1 into there, 1 squared is 1 plus another 1 makes 2. And you can see that that point there is 1, 2. And then next point here, if I x value of 2, put into there, 2 squared plus 1 makes 5. So if you put in an x value of 2, you get a y value of 5. Now, here's where we make a big jump. Historically, from what we understand, there was all sorts of working out that people had until two people come along, Leibniz in Germany and Sir Isaac Newton in England, and they developed the maths behind this and why it works. Now, people talk about that to get that area, we're getting the sum of a rectangle. Now, no one's totally convinced whether that meant it's the sum, but a lot of people believe it is. So we want to get the area, or the sum of the rectangles, if we had an infinite number of rectangles, so you can get the rectangle smaller and smaller in width. And we want it to start at x equals 1, and we want it to go at x equals 2. Now here's the interesting part. We've got the sum starting at 1 and going to 2. Historically, I'm convinced that people knew how to do this and what it did well before they had the actual proof for it. I always think of the case with people getting scurvy when they got on boats. They didn't know about vitamin C, but they knew that they could take fruits and tomatoes and all those sorts of plants, and they didn't get scurvy. So later on we found out about vitamin C. So now I'm going to write down, we want the area starting at 1 and going to 2, starting at 1 and going to 2, of the function that we're talking about, and the function we're talking about is that parabola, which is y equals x squared plus 1. Now I can work that out very accurately just by drawing it up on grid paper and calculating it, and then I can use other methods as well. But I want to show you how easy this is. People knew that if they went increase that power by 1 and divide by the power, let's have a look at what we're doing, talking about integration. I talk about the IIs. Now if you want to watch, I've got 9 videos at the moment on integration. You can go and learn the technique and what's going on. But this is the understanding of this area. That's all I'm looking for. So when we're doing integration, we increase the power. We increase the exponent. A lot of people say exponent. So the 2 becomes a 3, and then we divide by that 3. Now, if you don't understand that, don't stress over it at the moment, just watch what happens. People knew it was true, but they didn't understand why. The x, now by the way, if I wanted to, I could put x to the power of 0 beside it, because x to the power of 0 is 1, so you go into index laws, you go into everything here. This is your rule math. So I could write that as 1x to the 0. Now what's the rule? You increase the power by 1. So that becomes x to the 1, and then you divide by the power. So in other words, it's just x. Now we always talk about there could be another number as well. So if you want to go and watch my differentiation videos, there's heaps of them, and my integration videos, which is the reverse, you get that. So let's have a look what's happening here. Now, a lot of people will write 1 to 2. Some people will write it over here. Just whichever your teacher does, it's the same system involved. Now, I want to talk about this idea here. If I had, and I put this graph right across to here, what this system works on, it works on we're getting the blue area from 0 to 2. That's where that 2 comes from. And then we're subtracting the section over here, which I should call originally was white. So we're getting the big area, subtract not the red area, we want the red area, so we're subtracting this area here. And that's what these two calculations are. Just have a look what it is. So it means you substitute the 2 in place of the x. So 2 cubed, I'm going to shortcut on that because I want people to do it in their head, especially when it comes to negative. 2 cubed is 8, so that's 8 on 3, plus x to the 1, which is 2 to the 1 on 1, which is 2. Now what happens with this constant? I'm going to put a bracket around all of it. I'm going to put another set of brackets, and we're going to use the 1. So this is called substituting 2, and now we're going to substitute, a different tense, substitute 1. So watch what happens with 1. Put the 1 in, 1 cubed is 1. Put the 1 in, that's 1 to the 1 over 1, which is just 1 plus a constant. Now when I subtract those, now by the way, a lot of people like the square bracket, there's a reason for it. So let's have a look what's going on here. You've got actually 2 and 2/3 plus 2 plus c. Now watch what's happening here, minus 1/3, minus also 1, and minus also c. So I want you to understand that the c's, once you put numbers in, the c's eliminate each other. And we've just got a fraction calculation. Now I always talk about add the positives first, so that's 4 and 2/3. And then we're going to subtract 1 and 1/3, so subtract 1 and 1/3. Good part is the math numbers on that turn out to be quite nice, because you can just go 4 take 1 is 3, 2/3 take 1/3 is 1/3. So you've got 3 and a third. You can double check if you want. If you add those two together, you should get that. So 3, 4, 4 and 1/3, 4 and 2/3. So that area here is 3 and 1/3, and we talk about the unit squared because we don't always have centimetres or metres on there. So that's what the integral is. Now I believe and I understand they didn't have this terminology, but historically they knew that they could figure that out as exact as they could. So historically people would have been able to figure out probably that was 3.33. Could actually fairly accurately get that quite easily. And then they'd probably say to themselves, I think it's 3 1/3. And someone came along, this is what they had to figure out why it worked, and said if we increase that by 1, divide by the power that we increase it to, increase that by 1, divide by the power, substitute the n value and substitute the first value. Sounds like I'm talking double Dutch. You end up getting exactly the answer we're talking about there. And of course, like I've already said, a lot of people, no one knew why it worked until they figured it out. And the way they figured it out was by making lots of rectangles and figuring out the maths there. So there's lots to it. So what's interesting, because we're starting with a parabola, the area under a parabola turns out really nice. Not turned out to be some unusual decimal or horrible fraction. Amazing how often parabolas are fantastic. And we see parabolas everywhere in life. So that's the introduction to area under the curve, just starting with a basic integral. Now I'll see if I can do some more questions. So that's an introduction to area under the curve using integration, using integrals. I hope you appreciated it. I hope it helped you. Thanks for watching. Bye for now.